I remember the first time I saw Jack Harvey. It was, to my recollection, it was in the dining hall facility at South Pole Station. And I was working down there as an instrumentation engineer and setting up some stuff. And Jack, I knew about him. I read about him in Sky and Telescope magazine, and he was a real regular at South Pole. And he was a famous solar astronomer who ran this thing that tracked the sun 24 hours a day because the sun is up for months on end at South Pole. And so I had heard about him, and I looked at him, and he was sitting there with his team. And I was just interested in any other people involved with astronomy, but he just seemed at a glance a serious person, intimidating, I thought. And so we might have had some conversation, but this is the way I approached Jack Harvey. I had no idea that eventually I'd have other opportunity to become acquainted with him and realize he grew up as an amateur astronomer in the LA area and hung out at Mount Wilson Observatory as a boy. And if you go through the back pages of Sky and Telescope magazine, every once in a while you bump into a reference to Jack Harvey and one of his photographs and all his early astronomy stuff to understand just how wonderfully approachable he is, given how his interest in this goes back the way it does for so many of us. So anyway, Jack has become a dear friend. We've collaborated on some fun projects together, particularly one historical project involving this telescope. But he was at a meeting up in Colorado, and can you believe it, he and his wife Terry here were willing to loop down this way on their drive home. And because we had some things to exchange related to a historical project that's been ongoing a long time, but we think we're going to finally wrap up. But Jack had a gadget that he had built, and knowing of my illness collecting these kinds of things, he thought maybe this gadget would be appropriate to turn over to my stewardship. I think he probably thought it could be some form of therapy. You know how sometimes you have these things to squeeze in nervous anxiety, you know, they hand you these things at certain hospitals. But this is something one can look through, and I don't really understand much about it, but I think Jack is going to explain it to us.
Yes,
and
you'll all get a chance to look through it.
Look through it. So with that very curious introduction, I turn it over to Jack Harvey, for whom I just learned on the internet last night. Mountains are named in Antarctica, and also small worlds orbiting the sun. Yeah, I put some good stuff in the little announcement that you haven't seen.
Thank you, John. It's a pleasure to be here. Terry and I are enjoying our road trip, which is now 2,200 miles. And we were looking forward to coming here because John is a dear friend, and I always enjoy being with him. Always learn some new stories and things that I didn't know. And if you can go through a day and learn something new, it's always a good day. John invited me to give a talk about this device that I'm going to show you later. And I'm going to turn it over to his collection of antique telescopes because I'm becoming an antique myself. And I figured that was appropriate. I got to start getting rid of stuff. And while I was preparing a lecture for a meeting of astronomers in Costa Rica, I started working on this thing, thinking that because I was talking about the history of solar physics, that it would be interesting to try to replicate what some of the early solar astronomers did way back in the early 19th century. And I prepared a talk for our astronomers in the Tucson area who are interested in all kinds of solar stuff. And it's a lunch talk, so it's pretty informal, but it's aimed at astronomers, so I'm going to perhaps lapse into jargon that I don't want to do. Since this is so informal, I want you to ask questions at any time, or if the words are getting weird, let me know and we'll try to downsize. So the first thing I better explain is polarimetry. Living in New Mexico as you do, you know all about light and color. And light has intensity, it has color, wavelengths, but one of its more subtle aspects is it has polarization. What does that mean? Polarization is a property of light that it tends to vibrate in a particular direction. We can't see it with our eye, except for one thing. And alcohol helps too, I should point out. If you look at sunset, if you look about at the zenith, 90 degrees away from the sun, some people can see something that's called Haydinger's brush, which is kind of a cross blue and yellow. And the eye, the center part of the eye is sensitive to polarization. The sky at that condition, near sunset, at the zenith, is highly polarized. So your eye can actually see this. And I first explained it to some of my colleagues with alcohol involved. They thought I was crazy, but they eventually could see it. So that's about the only way we can actually see with our own eyes polarization. But again, it's a property of light that carries a lot of information. A lot of information for astronomy comes from the intensity of light and from its wavelength, but a lot comes from polarization. And I'm interested in polarization because my specialty has been magnetic fields on the sun, which I've been studying for 60 years now. Scary. In order to measure magnetic fields on the sun, we have to take advantage of the fact that the magnetic fields on the sun change the polarization of light around certain spectrum lines. And we measure that polarization and can infer what the magnetic field is. And so that's been keeping me in business for about 60 years. So I was interested in the history of polarimetry as applied to the sun. And I started researching it in order to give this talk, not this one, but the one in Costa Rica. And I got really interested in the whole subject. So that's what I'm going to talk about here. And then we'll talk about the instrument that I built. It's a replica of one of the early polariscopes. And let's see if I can make this thing work. Yeah, well, let's see. Again, this is not aimed at you, but my colleagues. Why do we study polarimetry and the history of it? Well, as I explained, in order to learn much more about the sun than we can, if I'm in the way, I'm sorry, we need to exploit the polarization of the light. No other way is available to learn some of these factors or features about the sun. And as I said, I was invited to give a talk about this. And the history goes back 200 years, which really surprised me. I thought maybe it was only when I was born, when I started in the field, but that turns out not to be the case. And I've only been doing it for a quarter of the time of the history of this field. But before talking about solar polarimetry, and I should explain again for those that just come in, that what we're talking about is polarization of light, which is a property of the light that it tends to vibrate up and down, left and right, or even circularly. And we can measure that with instruments, although it's very hard to see with our eyes. Well, the dawn of polarimetry itself goes way back to Rasmus Bartholin, which he has a really impressive head of hair. So he was playing around with crystals of calcite, which were known at the time. They called it Iceland spar, because the best crystals came from Iceland. And I should have brought one with me. I'm sorry I did not, forgot. But he noticed that, as had been known for a long time, that when you put a piece of glass, a thick piece of glass, and shine a beam of light through it at an angle, it deflects the beam. There's something called refraction. And but Iceland spar is different. it produces two images of the light going through it. Perhaps you can see that here, one there, another one there, or the line under there is doubled. And he found that that was really interesting and wrote a 60-page treatise on the subject in 1669. And if you've got a copy of that in your collection of books, you want to guard it because it's very expensive now. It's already selling for $10,000.
I don't have that one, unfortunately.
Too bad.
I think of the party we drove the soul.
So there at the end of the 17th century, and there was a flurry of activity, mainly sparked by Bartholin's book, and people were really interested in it. Another guy, Christian Huygens, also with an impressive head of hair, tried to explain this property, and he did in another book here, which is even more expensive, $20,000 for this one. And as a student long, long ago, when I was learning optics, one of the first things I learned is Huygens' principle, in which he imagines the passage of light through matter to be a succession of emissions from points inside the matter that travel in spherical wavefronts. And I took a picture of a laser beam, in fact it was this laser beam, going through a piece of calcite. You can, I hope, see that it splits into two pieces, two rays. Well, his explanation was pretty good. And he unfortunately didn't publish it for a while, kind of kept it to himself. But he visited Isaac Newton in 1690, and he detected that Newton was onto the same thing. So he said, I better protect my priority by publishing it. So he published it right after he visited Newton and got the priority. So that's how polarimetry got started in the 17th century, and then another century passed and hardly anything was being done. Centuries come and go. Sometimes there's a lot of progress, sometimes there isn't. But at the beginning of the 19th century, this guy popped into the area. Etienne Louis Malus was an engineer in Napoleon's army and a smart guy. He got injured in a battle and was recuperating in an apartment opposite the Luxembourg Palace in Paris. And he was playing around with a piece of calcite and looking out the window, and the sun was setting and the reflection was coming off of the windows of the palace. And it was just by chance that he noticed that he was playing around with this calcite piece. He detected that the intensity of the light he was seeing looking through the calcite was changing as he rotated it. And he said, aha! He said, this is important, I need to write it up. And so he did. He published this paper in 1808. And you can find this online if you read French, it's pretty interesting. Here's his portrait, kind of a stern-looking guy. He built a simple polarimeter. What he had detected was that as light is reflected off of a piece of glass at the right angle, it becomes polarized. So unpolarized light coming in, and after the reflection, some of the light goes through the window, of course, but the reflection tends to be rather polarized. So that's what he detected. And in fact, he introduced the term polarization, which we use commonly now in science. So there it is, his term. And he built a simple polarimeter consisting of two pieces of glass, which he knew polarized the light. And he could change the angles of the glass in and out and rotate the things around and study the character of polarization. And in fact, we have in optics now something called the law of Malus, which tells you how much light gets transmitted through polarizers. So he's remembered for that, not for his military exploits.
So will a mirror polarize light too, in the same way?
I'm sorry?
Will a mirror also polarize light in the same way?
It does, but not the same way. Mirrors tend not to polarize as much as just a plain piece of glass. And it depends on the coating on the mirror. Silver polarizes more than aluminum. And mainly it's a nuisance for us astronomers because our mirrors are coated with these things and they polarize, and we don't like that unless we really want to study the polarization. Well, Malus was friends with a guy by the name of Francois Arago, and Francois Arago has another very interesting history. He was in the military, sort of a spy, might as well call it what it is. He was a spy, and he got caught by the Spanish, was thrown into jail for a while, but he had an illustrious career after that. I think he was bailed out or something. I can't remember how he got out of that jail. But he got back to France, and he was a scientist of the first rank. He started a series of lectures at the Paris Observatory, which is continuing now. He built up the Paris Observatory, became its director, and among many of his other feats, he was the premier of France in the mid-19th century. And one of his favorite things is he freed all the slaves that were in the French colonies. He was kind of Republican in that way. Another odd thing about him is his signature. You see quite a flourish at the end. Turns out that flourish, if you look at it at the right angle, is Arago.
Oh.
So he has his name twice there. And it's fun to look at his writing because it's very florid like that. So he's a famous guy in French astrophysics. And I thought he might be the father of astrophysics in France, but I talked to one of my colleagues in France, and he said, no, it's another guy whose name will appear later. But I still think he made huge contributions to astrophysics in general, and certainly polarimetry. The France essentially controlled all of polarimetry for about a century, and it started with Malus and then continued with Arago. So what did he do? He built a polariscope. A polariscope is a device in which you can look through and tell whether the light coming into it is polarized or not. And that's the replica that I've built. We'll look at it later. But his first version was not as advanced as what we've built here. But he used a piece of calcite crystal, and a piece of mica. And when appropriately put together, you can tell by these images below whether light is polarized or not. I took these pictures in my lab to show you. Here you may see a blue circle. The calcite, of course, produces two images. The light's going through two different ways. One of the images is polarized one way, the other image is polarized opposite to that. And with the mica underneath, it becomes colored. And so we have blue and orange. And if you rotate the calcite just right, both beams have the same intensity. And if you keep rotating it, you see you get back to orange now and blue. So looking for those colors gave him a way of telling whether light was polarized or not. And by putting a piece of glass in front of this thing and tipping it right, he could cancel out polarization and measure the angle of his glass and make quantitative measures. His later version, which is the one I've replicated here, was about 1809, and it still exists in the Paris Observatory. The replica I've made is only of the polariscope part, not any of these auxiliary things. John would love to have his hands on this, I'm sure.
I think we all would.
Yes. But it was a quantitative instrument. He was able to make measurements that could be repeated and tested and compared. Here's his 1811 version, very similar to the 1809 one. And how does it work? Well, among the many things that Arago discovered was that if you have a quartz crystal, and maybe some of you have seen large quartz crystals, they have sort of a hexagonal cross-section and pointed at the ends. And I should have brought one of those too, sorry. But the pointy part, the ends, represent the optical axis of quartz. Quartz crystals has the property of behaving rather like calcite and splitting up the light into different directions and polarizations. But there is an axis. And if you polish off the ends of a quartz crystal, Arago discovered that if you put white light in, unpolarized light in, it gets rotated a little bit. And the blue light gets rotated more than the red light. And we call that optical activity. I don't know why activity, but that's what it's called. It seems like optical rotation would be better. But he had discovered that rotary dispersion of light into colors whose angle is a function of the color. And he decided to build a polariscope based on that principle. And so by combining a piece of quartz that's cut properly and polished right, so that light going into it rotates depending upon its color, more for blue, less for red, and a piece of calcite, or actually at this time, since optical activity in France was so vigorous, a couple of guys had come up with special prisms that would split the light into two polarized beams better than calcite did. So he combined one of those prisms, a so-called Roshan prism. That's another story. Roshan was a cleric in France, and his hobby was optics and crystals. And now he's remembered for making these Roshan prisms. And that's what's in the device. One of these quartz plates at one end and a Roshan prism at the other. And with some training and looking around at various features, it's pretty good to about 5% linear polarization. And that was a huge advance at the time. We didn't know how much light was polarized. Right now we are measuring polarization in 1 part in 10 billion. The advance of technology, not because we're smarter. Now, sorry. He added lenses, essentially a telescope, making a telescope out of this, and he called it his polariscopic telescope, La Lunette Polarimétrique. And I don't have those extra lenses. Now again, this is sort of the progress of what the colors look like in the nearly overlapping images. As you rotate the plane of polarization of the light passing through the device, that's just a series of different angles of the rotation and polarization. And here I have a little animation that shows what polarization does through one of these quartz plates as a function of the angle of the rotation of the light. And this is an animation. We'll see if we can make it go. Now we're rotating the plane of polarization through. And you see the colors in the central part are changing from white to red to blue to white again, gone 180 degrees around. So it was based on that color change that Arago and other scientists of the day were able to measure polarization. Now this optical activity got people really interested, and you wondered, what property is it about matter that will let polarized light come into it and rotate it? How can that possibly happen? And essentially the story that came up with was that the molecular structure inside quartz, or the atomic structure, is a helix. It's essentially a spiral, not like DNA, but smaller on scale, of course. And the light is vibrating depending upon the properties of the atoms and molecules, and it gets rotated depending upon the helix. And it turns out that quartz has 2 kinds of helices. It can be right-handed or left-handed. For reasons that I don't know, all of the optical instruments these days are made with right-handed quartz. Maybe the left-handed quartz is hard to find, I don't know. But one has to be careful in studying this stuff to make sure that the results are depending upon which type of crystal you're using. So anyway, there was a lot of interest in what matter rotates this polarization. And people were looking at all kinds of things, like liquids, various crystals, glasses, and then they got interested in gas, what vapors might do. And so this guy, B.O., set up an experiment. And he wanted to see if turpentine gas would rotate the plane of polarization, like the quartz crystals do. Well, it's very low density, so he didn't expect to get much action over a small distance. So he set up this 30-meter long tube, and it's a good thing it was the old church. At one end he put the polarized light source and a boiler to boil the turpentine and fill the tube with vapor. So that's this end. There's his light source and there's the boiler. And he put the light into this long tube. And he was sitting at the other end. And what happened? You probably can already guess. So he was looking through this thing and was about to make the measurement when the boiler blew up. And nobody was hurt. But he was pretty sure the turpentine was rotating the light. But he wasn't about to do the experiment again. He's a very smart guy. So he encouraged others to repeat the experiment. But he gave them a warning. And you can see what the warning is. The explosion of vapor could cause persons at some distance to perish miserably. So it turned out that the rotation of light through gases and especially biological materials has been very useful and is studied greatly today. But these kinds of experiments are not done. Now, you've all heard of Louis Pasteur. He studied the properties of rotation in tiny little crystals. And he noticed that the crystals had different forms, two forms. And through a microscope, he separated the crystals according to their form into two piles. And then he discovered that, and he said he's made this great discovery, he discovered that the crystals that were in one form rotated the plane of polarization one way, and the other form of the crystals rotated it the other way. And he was absolutely thrilled for that discovery. And I've just made a great discovery. I'm so happy. I'm shaking all over, and I'm unable to set my eyes again to the polarimeter. And of course, Pasteur went on to other fame that we're much more familiar with, but I thought that was particularly charming. Now, I'm going to turn to the use of polarimetry on the sun. Well, Arago was a great scientist, and he used his polariscope to study the light of various sources. You heat up iron to incandescent temperature. You would look at liquids, you'd look at flames, and what he found was that liquids would actually polarize light a little bit, and certainly incandescent solids did quite a bit, as long as you were looking at the light from an angle. The light coming from these sources was polarized. But from flames, he couldn't see any polarization. Then he turned his polariscope to the sun, wondering what he would see. And he looked near the edge of the sun in particular because he knew that light was coming out at an angle there. He saw no polarization. And from that, he concluded it must be more like a flame than a solid or a liquid. And he reported that the solar surface was gaseous. But I don't know why he waited so long, but it was 1811 when he did the observation, but he reported it in 1824. And let's see, the French says, the visible part of the sun is thus a material of gaseous incandescent nature. And so he was the first one to demonstrate that the sun was gaseous. Even later in that century, some people thought it was still solid or even liquid. There's a guy named Zollner who thought that the sun was liquid and produced a big treatise on it. And some people didn't actually agree with Arago, but eventually his demonstration was accepted as representing that the sun is gaseous. Now, there was an eclipse in 1842, total eclipse of the sun. By the way, next year will be a nice eclipse of the sun, and I hope some of you, if you've never seen a total eclipse of the sun, will have the opportunity to see that. It's a glorious spectacle of nature. We're going to do it. Anyway, in 1842 there was a total eclipse, and Arago, of course, and some of his buddies detected linear polarization in the corona of the sun, the outer atmosphere. But there was ambiguous nature of that. It wasn't quite clear what was going on. But then a guy from Sweden, Edlund, in 1851 repeated the experiment, and he confirmed that it was polarized, and he showed what direction the polarization was. It was radial to the sun's center. And that was confirmed again at another eclipse in 1858. And finally, it became accepted through history and more demonstration science that yes, the sun's corona is gaseous and it's polarized. Then in 1879, one of the theoreticians made a theory that explained it all, and we still use his theory. He thought it was scattering particles of dust. We now know that it's electrons. The corona is very hot, and so dust doesn't exist there. It's boiled off, basically. And there are free electrons all over the place, and highly ionized atoms of other materials. So the typical observation in those days would look something like this. Oops, sorry. You have two images of the corona through the polariscope, and one of them would look a little different than the other one. This etching I got out of an old book doesn't show much difference that I can see, but they were demonstrating what the observation looked like. So even more, one thing you can see at total solar eclipses are the prominences that stick out above the edge of the sun, and they're glorious. They're brilliant, lilac-colored, reddish-colored blobs that look like clouds. And there was much interest in these in the time. Are they polarized? Too? Well, they weren't detectably polarized according to many observations. And it took the Frenchman Bernard Liot until 1934 to be able to measure the actual polarization in the prominences. Bernard Liot was a genius of optics and astronomy. It turned out that essentially the polarization was too weak to be able to be detected by visual means. But we now use polarization of prominences to understand what the magnetic field is like, the dynamics of prominences, how the motion of the gases is going. And I'm going to pretty much end this part with something that's not very far away. There used to be a lot of research on solar radio polarimetry in the 50s and 60s. Solar radio astronomy kind of died out or became dormant then. But right at the VLA, you might have noticed, if you visited recently in the last few years, that there's this field of, looks like my wife called them teepees, little teepees about yay big. And this is a much denser array than the VLA itself. And so it's able to make an image in radio wavelengths of the whole sky. And it produces two images, which you can see on the internet, about every few seconds. And it shows the radio emission coming from the entire sky, not only in intensity, but also in polarization. And if the sun is active, the sun becomes very bright in this image, and the polarization usually becomes very bright too. Because when the sun is very active, it's usually emitting some gas or blowing something off in a way that's asymmetric that tends to produce polarized radio emission. So I find this site fascinating to watch, to see what's going on. You can log in anytime, except when they're doing special experiments. And here's one of those special experiments. A friend of mine from the VLA facility gave me these unpublished observations. And what we have on the left is radio frequency here from about 25 megahertz to 85 megahertz. And this is the intensity of one of those emission events from the sun, and all kinds of interesting structure as a function of time. So the frequency and time. The lower frequencies come from higher up in the corona of the sun. The higher frequencies come from lower down. So we see features drifting from early time to later time as they're going up into the corona. Same sort of thing here, drifting to the right, higher. But what's really interesting, to me anyway, is the polarization of this structure. It's quite different from what we see in intensity. And unfortunately, not enough people have been studying this stuff recently. But interest is picking up. And we have to use the polarization and the intensity to understand the nature of the gas rushing up from the sun, which sometimes gets to us. And that's the end of that one, but I've got another one. Sorry, you can't get out yet. And this talks about the polariscope.